Okay, so question 2 is naming. So it's organic compounds and it's the naming part. And again, as they do with physics most of the time, you start with the definition. So I'm just going to show you the definition because I don't really know that one out of my head. So an organic compound is a molecule or compound containing carbon. So you get 2 marks for basically writing 2 or 3 words. You really need to learn your definitions. Oh, you only get 1 mark. That's disappointing. Anyway, so organic compounds are ones that contain carbon. Then, if we get to the interesting part, they want you to write down the name of the following. The IUPAC name is basically just the system that you've been taught. So you don't need to worry about IUPAC. What you can do, what I'd sometimes tell my class to do, is basically just, if you're stressed about what is IUPAC, if you cross that out, write down the name of the compound. I can do that. So don't worry about the IUPAC part. But basically they're telling you to use the system that was taught to you, like you have any other option. But anyway, so now for compound E, I don't like how they do this, but anyway, step 1 is find the longest continuous chain of carbon to carbon bonds. And we need to include the double bond in that chain. So if I can just redraw that quickly, I wouldn't suggest you redrawing it unless you really know what's going on, because I don't want you to lose marks because you redrew it incorrectly. But if I can just color it in quickly, so if this one is the red one, then this one would be the red one. This one will be the blue one, which is that one. This one will be the green one, which is that one. And then the yellow one could be either that one or the other one. But if you're going to redraw them, I suggest you do it carefully. However, while you're studying, if you always redraw them, you'll obviously get better at it, because anything gets better with practice. There is another CH3 that comes off the blue one. We can see from us coloring in. So there's another CH3 that comes off there. We should know that anyway, because we know that carbons need 4 bonds. So this red one has 2 bonds to hydrogen and 2 bonds to the blue carbon. This blue carbon has 1 bond to the green, 2 bonds to the red, and the 4th bond is to this one up here, which I haven't colored in. Then the green one is bonded once to the hydrogen, once to the yellow one, once to the blue one. So that one has also only got 3 bonds. But then again, if we look here, there's another CH3 that comes off the green one. So now we need to add another CH3. So now to name it, the longest continuous chain of carbons is 1, 2, 3, 4. So that means that this thing is bute. There's 4 carbons in the longest continuous chain. There is a double bond on the first carbon. It's between carbon number 1 and carbon number 2. Because things that change the parent chain. So if I can just write them here, ene, ol, al, oic acid, one for a ketone, anything that changes the name of the parent chain. I sometimes say in class like the surname, the second word. That is automatically more important than the add-ons. We have added on 2 methyl groups, so that makes it dimethyl. So it's dimethyl because there are 2 methyl groups, and they are on carbon number 2 and carbon number 3. You need to have the lowest numbering possible. If you numbered it from the other side, this would be 1, 2, 3, 4. The methyls would still be 2, 3, so this wouldn't make a difference. However, your double bond would be between carbon number 3 and carbon number 4. We need the lowest possible numbering, and the double bond part is the most important. It has the highest priority. So therefore, the name for E is going to be 2,3-dimethyl-but-1-ene. Okay, then for H is a ketone. I don't know whether you can tell, but there is a C double bond O, which is, you find it in an acid when it looks like this. You find it in an aldehyde when it looks like this. And you find it in a ketone when it looks like this. So essentially those are the diagrams of the functional groups of the 3. You have to make sure that your carbons have 4 bonds. I should probably show that bond there. And so this is the acid, this is the ketone, and this is the aldehyde. H is a ketone. There are 4 carbons so it's bute. They are all single bonded carbons, so it's AN, not EN or YN. And on the second carbon, there is a ketone. The ketone can't really go anywhere else, so you don't really need to say the two. You can see that there, they didn't say the two. Because the thing is, if you, I don't know whether you feel like doing this now, but if you moved this double bond O to here, it would be an aldehyde. So it wouldn't be a ketone anymore. If you moved it to here, it would be an aldehyde. If you moved it to here, you would number it from the opposite side, and it would still be butan-2-one. So put in numbers. You never put in numbers for an aldehyde. You never put in numbers for an acid. But if you put in numbers for just about anything else, no one's going to have an issue. Butan-2-one is as correct as butanone. You can see it there for the memo. But it's just, it's not that it's wrong to put the number in. It's just what is called, like in English, it's redundant. Because it can't be anywhere else. So why are you telling me it's on the 2? It can't be on the 3, the 4, or the 1. So there's no need for you to tell me the 2. However, I would suggest you always put the numbers unless you're doing an acid. No numbers for an acid. It's always carbon 1 or an aldehyde. No numbers for an aldehyde. Always carbon 1. Okay, so if we carry on here now, we get to 2.3. What is the structural formula of compound B? So I prefer actually doing it this way. Compound B, you need to draw it out. So again, we spoke about it earlier during the multiple choice, but this is 3 CH2s. So that is in the chain. 1, 2, 3. The difference between that and if you had something like this, it's a very subtle difference, and the only reason why I can see it is I've done a million examples of this. This is a CH2 and there are 3 of them. It looks like this. This is a CH3 and there are 3 of them. Okay, well I've actually... So what you would need here, you would need it to do this. You would need 3 CH3s stuck on, and then you would need an H or something. So this guy needs an H, just so it can have 4 bonds. If you have multiple CH3s, it's add-ons. If you have multiple CH2s, it's just a longer chain, because the carbons in the chain end up being CH2s. So now I need to add their 2 H's, so there. And you see, so far, all of the carbons have 4 bonds, except for this last one. This part over here, it means it's an ester. That is an ester. And if you see here, you need to draw it like this. I don't know whether you can tell that, but this COOCH, this here, the carbon that has no hydrogens on it is the one that has the double bond O. See, this carbon on the right-hand side has 3 hydrogens on it. This one cannot be the C double bond O. And now, as a last step, you need to add all of your H's. If you forget an H, you're going to lose a mark, so please don't forget an H. But if you add all of your H's, you then have your ester. I don't know whether they're going to ask you to name it, but it's methyl pentanoate. It's 5 carbons on the one side and 1 carbon on the other. And the C double bond O is always the surname, the second word. So that would be methyl pentanoate. I'm not sure if they asked you for it, but here is its structural formula. You get a mark for drawing the correct functional group because it's an ester, and then you get a mark for everything else being the same. Then for 2.3.2, they ask you for, let me just move this quickly. 2.3.2, they ask you for the structural formula of compound C. So compound C is 4-ethyl 3,3-difluorohexane. So that sounds a bit hectic, but what you do is 1 bite at a time. Difluorohexane, hex, 1, 2, 3, 4, 5, 6. Hexane. Difluoro means there are 2 fluorines, and they are both on carbon number 3. So there are the 2 fluorines. Please don't do FL. Fluorine is not FL. Look on your formula sheet. It's F. Look on your periodic table. On the 4th carbon, there's an ethyl, which is a 2-carbon chain. So that is the skeleton of what we've needed to do, the structural formula of compound C. And now, afterwards, you need to add your H's so that every carbon has 4 bonds. So this one needs 3 H's, this one needs 2, that one already has 4 bonds, this one needs an extra 1, this one needs an extra 2, this one needs an extra 3. So basically, we're just making sure that every single carbon has 4 bonds. Take a minute and just double check. I know you're absolutely exhausted by this point, but if you can just double check, because you are going to lose a mark for leaving off an H, which you don't need to do. You don't need to leave off an H, although I suppose they didn't need to ask you to draw so many H's. But that is going to be your answer. Sorry, I should just show you the memo, but anyway. So see, there he is there. So you get a mark for 6 carbons in the longest chain, so that's the hex. 2 fluorine atoms on the 3rd, and then an ethyl on the 4th. Then if you leave out an H atom, it says there that your maximum is going to be 2 out of 3. So you can't leave out any bonds, you can't leave out any hydrogens. You must take your time with this question, I think. It's not that difficult, but it is a bit finicky about what you need to do in order to get the marks. So just don't make silly mistakes, please, if you can help it. Then, the last one for this, I think. The general formula of the homologous series to which compound E belongs. So compound E is this bad boy over here, and it is an alkene. It's got a double bond. So you could just count what's going on there, or you could have studied it. It's CnH2n. If you don't want to count what's going on here, and you don't want to remember it, what you do is you just draw the smallest ones. Here are the 2 smallest alkenes. There are the 2 smallest alkenes. This one will have 2 carbons and 4 hydrogens, if we just draw it quickly and make sure that each carbon has 4 bonds. This one has 3 carbons. Oh, sure, but I've done too many already. Silly. It has 3 carbons, and it has 1, 2, 3, 4, 5, 6. So this is 2 carbons, 2 hydrogens. This is 3 carbons, 6 hydrogens. Therefore, in general, an alkene is CnH2n. So if you don't want to learn your general formulae, you just take the smallest ones, you just draw them out quickly and just count. Then they want the structural formula of the functional group of compound F. So now you maybe need to be careful again. Oh, sorry, I haven't shown you on the memo. Silly. Okay, so that's CnH2n. Now they want the functional group of a ketone. How do I know it's a ketone? It has a C double bond O. However, it's a bit more detailed than that. It also has a carbon on that side and a carbon on that side. If it has a hydrogen on one side, it's an aldehyde, not a ketone. And now we need to follow the golden rule of organic. Every carbon must have 4 bonds. It doesn't need to bond to anything, but you better draw your carbons with 4 bonds. See, there we go. So they didn't really like this one. They accepted this one later, so I'd rather we do this one. And you get 1 mark for all of that, which I suppose is quite a lot of work. So now just to go on to the next one, 2.3.5, they want the name of the alcohol to produce compound B. So if we go back to 2.3.1, I told you that the part with the C double bond O, so this part here, let me just highlight quickly. So this part here is the acid. This is the surname, the second word. The C double bond O part is the acid, and the part without the C double bond O is the alcohol. There is 1 carbon in the alcohol, so that means that the acid was pentanoic acid, or was 5 carbons, and what they're asking you is the name of the alcohol. The name of the alcohol is methanol. That's quite nice, because if you say 1 methanol, though, you see there you only get 1 out of 2. Again, you don't need to say the 1 because there is only 1 carbon, so you don't need to specify that it's on number 1. But you get 2 marks for just saying methanol. So the IUPAC name of the alcohol needed to produce compound B, it's this blue part here. It's a 1 carbon alcohol, and so it's methanol. Then for 2.4, they want you to write down the name of write down the letters of something that is a functional isomer of G. G is an acid. I don't know whether you're aware, but G is an acid. This part here makes G an acid, and the functional isomer of an acid is an ester, always. There are 1, 2, 3, 4, 5, 6 carbons in that acid. There are 1, 2, 3, 4, 5, 6 carbons in this ketone. There are 1, 2, 3, 4 carbons here, so definitely not that one. Hexanoic acid, see now this one and this one both have 6 carbons and they're both acids, but that doesn't mean that they are a functional isomer. Functional isomer, we need to study maybe. It is simply a ketone and an aldehyde. So an aldehyde is a functional isomer of a ketone. A ketone is a functional isomer of an aldehyde, and an ester and an acid. An ester is a functional isomer of an acid, and an acid is a functional isomer of an ester. So G is an acid. This is not a functional isomer. That is a chain isomer, I think. Yeah, because the chain here, the continuous chain is 1, 2, 3, 4. So this is 4 carbons in a row. This is 1, 2, hexanoic acid will be 6 in a row. So this is 4 in a row, this is 6 in a row. It's a chain isomer. This is not a functional isomer because this is a ketone. This one here, we drew it out again. That was an ester. So an acid is a functional isomer of an ester. It must be B. It's the only ester that's here. And it's 5 carbons and 1 carbon. 5 and 1 is also 6. So B is a functional isomer of the acid, which has 6 carbons in it, because B is an ester that has 6 carbons in it. 2.4.2, chain isomers of each other. It's D and G. It's D and G because D is hexanoic acid. It's an acid with 6 carbons in a row continuously. G is an acid with 4 carbons in a row with these 2 carbons added on. They're added onto the chain. So there's 6 carbons in total, but the longest continuous chain of carbons is only 4. So the chain isomer, this one would be bute, this one would be hex. That's why it's a chain. There's different chain lengths, making it a chain isomer.